Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so I'm going to talk about a project we've been doing over the last, I'd say, 18 months to a year. And it's sort of we're building a big system, and I just want to start off with recognizing, I think, the set of people we work with. This is a mix of, essentially, I think, people who are in our ops groups or engineering team, like Vijay Gill, Dave Malls, Liwa, and Mohan. Some of us, I think Shrikant and Ming are with me in the networking research group. Roger Wattenhofer were visiting us from ETH, and then we have a bunch of interns working with us, right? Okay, so to set the problem context, the context is the following. So Microsoft, like any cloud provider, basically operates what's called the inter-DC WAN. This is the wide area network that connects our data centers. As you might imagine, this is, by the way, a made-up picture, just so you know, don't go looking for Microsoft data centers there. There are two things to this. Like, this is, as you might imagine, it's a highly critical resource for any cloud provider. It's highly critical because our services send traffic for both performance and reliability across the data centers. And so if you think of things like geo-replication in Azure, every write that comes from a customer gets replicated to another data center. If our users are doing queries and the entire index is not present in one data center, that essentially gets, queries essentially go across this network. So we need it both for high performance and high reliability, so to speak. At the same time, it's a very, very expensive resource. It's expensive because we have essentially hundreds of gigabits per second capacity going across oceans and going across continents. And this capacity is very, very expensive. So unlike the capacity within a data center, capacity across data centers, it's actually very hard to even upgrade. Right now, there's a big crunch about the optical capacity that's available across the Atlantic or in the Pacific or even in some parts of the US. So it's not just about cost, there's also availability issue. So given that this resource is very, very expensive, by the way, the amortized cost of this network runs easily into hundreds of millions of dollars per year. And this is taking off all the cost factors into account. So here's the problem we kind of became interested in. And the way we started working on this was actually Vijay came to us about a year or more, over a year ago, and he's basically said, like, you know, unless we can make this network highly efficient, we are basically losing competitive edge to other players that can operate the network a lot cheaply. And in particular, basically what goes on in these networks, and this is just it's a problem that's not unique to Microsoft. If you read about studies of people operating IP backbones, it's not uncommon for the average utilization on that backbone to be very low. So it's so low, in fact, that even the busiest links, the average utilization on the busiest links is less than 50%. The median utilization tends to be around 30% or so. So basically, we've built up this expensive resource, and we can use even less than half of it on a good day on good links. And that's essentially what's happening. So the question is, like, why does that happen? So one reason is this, which is that I think the way the technology stack of how these networks are built works today is that we have different sets of services using the network. These services, they send traffic whenever they want, however much they want. The result of that is we tend to see these diurnal patterns that you see here, that traffic essentially peaks, then it drops, such that peak to mean ratio is about, it's more than a factor of 2. So the reason this is happening is we have uncoordinated transmission by services. Now, if you don't want the network to drop traffic, you provision your network for the peak capacity. So you basically provision for peak, and then in average case, you have really low utilization. So you may look at this graph and go like, well, what can you do here? But the thing is, because we run the network, and because we run the services in our data center, and because we understand the nature of the traffic we are carrying, we can actually take a careful look at what exactly is happening. In particular, a very simple heuristic, we can separate the traffic into what you might consider background traffic or non-background traffic. So non-background traffic would be things like queries going across data centers or Azure geo-replication. Background traffic might be things like entire clusters being replicated from one DC to the other. So in average, what you see here, this is, by the way, like real traffic trace from one DC, one inter-DC link in our network. So what you see here is that the background traffic's there and a mix of non-background traffic, and there essentially that's what kind of determines the peak. But the nature of the traffic is such that the background traffic can actually be slowed down. So what we can do is that when the non-background traffic is peaking, to not carry a lot of background traffic, and we can carry background traffic when there's ample capacity in the network. So by doing that, if we can do that successfully, so what's going on here is that we can actually either now carry more red traffic, which is non-background, or we can essentially delay any kind of capacity upgrades that may be needed in there. So that's kind of like one source of inefficiency that we like to get rid of. The other thing that's happening is that the way these networks are operated today, they essentially do what you might consider like highly local, highly greedy allocation mechanism. So this is using MPLS for those of you who understand MPLS, but it doesn't really matter if you don't know how MPLS works. Here's what MPLS roughly approximates, right? So let's say given this network, a flow comes in from A to E. What MPLS will do for you, it'll find the shortest path that has available capacity to carry the flow. So in this case, it's that. Now if a new flow comes in from C to D, because the link CD is taken, it'll find the shortest path with available capacity. Because it's doing this local allocation, it does not have the freedom to move the blue flow in this case, or the router C does not have the freedom. So now a CG flow starts, and you basically end up with this. So what ends up happening essentially, that you get into this jumble of traffic where flows are going over longer paths than necessary because you're doing these local greedy allocations. If you had a global view of the network, here's what you should do, or you could do. Essentially, not only your performance will be better, you are using fewer links in the network, and a lot of other links, as you might see here, have been freed up to carry even more traffic in the network, if you could do that. So these are essentially the two sources of inefficiency that we're going to try and tackle in our design. I call SWAN, which stands like that for software-driven WAN. And what we want is a highly efficient WAN. So by the way, one thing I did not mention, efficiency is only one side of the coin here. It's very, very easy to eat up the utilization of the network. All we have to do is to let loose all background services we have, and the network utilization will go to 100% in no time. And the reason you cannot do that is because you have other traffic to carry as well. So this basically is the second goal of what we call like support flexible sharing policies. In particular, when we talk to operators and we talk to service developers, what matches our context is be able to strictly prioritize, let's say, things like interactive traffic over non-interactive traffic, non-background traffic over background traffic, and that kind of formulation maps to strict priority classes as to how resource allocation should happen. And within a priority class, there's an expectation by service owners and operators of fairness, that if you belong in the same class, like interactive class or background class, fairness is expected from the network. So we're going to take that as our flexible sharing policy. So what we want is a highly efficient and highly flexible WAN. And the key design elements, of course, are basically I'm going to coordinate the sending rates of services, and we are going to do centralized resource allocation because of the things I mentioned here. Quick show of hands, like how many of you know what SDNs are? 1, 2. OK, so I'm going to skip this. Anybody does not know what SDN is? It's OK to raise your hands. OK, I'm going to skip this then. Sometimes you know what's happening in SDNs. We are replacing beefy routers by commodity switches, and we are centrally controlling essentially what these switches do by directly programming their forwarding information, forwarding tables. That's it. OK, so here's an overview of SWAN. Here's what happened. So the way to understand is basically we've got two ends to the system. One is the service hosts themselves, and then the network. What we're going to do is, in the SWAN controller, this is like, logically think of it as like one controller in the network. We are going to get traffic demand estimates from these things we call service brokers. So service brokers take, a service is basically, from our purposes, a collection of hosts doing something jointly. Let's say they are replicating traffic, or they are serving user queries, and so forth. So these service brokers are going to estimate the demand, and they're going to tell the SWAN controller how much they need. So this happens for each service across each pair of data centers that we have. We are going to have these things called network agents that talk to the switches and tell us what the topology of the network currently looks like and what traffic currently happens. What SWAN controller does is that it takes all of these inputs and essentially computes how much each service can send at this particular point in time, and it reconfigures the network to carry exactly that. So we have a demand matrix, we compute the allocation matrix, and we reconfigure the network. So basically, and by the way, the final thing here is that the bandwidth allocation gets pushed down to the host, and any rate limiting happens at the host, because in the network, we don't have any capability to do rate limiting on commodity switches. They are not enough queuing capacity, or number of queues there is very, very limited. So that's essentially what we're going to do. Essentially, the thing that's happening here, in case it wasn't clear, is that every 5 minutes or so, what we are doing is redoing this computation and changing the network's configuration to match the demand matrix as best as possible. So as you might imagine, if we try to do that, these are the kinds of issues we run into. And the technical part of the work is essentially focused on, so that was kind of the architectural slide in terms of the algorithmic work for the work focused on solving challenges like these. One was like, how do you scalably compute bandwidth allocation and network configuration every 5 minutes? So we are talking about hundreds of services across at least tens of pairs of data centers. And basically, we have to do fairness as well as strict priority classes. So that's one challenge. The other is avoiding network congestion during updates. What I mean by that will become clear when I have slides explaining what the challenge is. And the other thing is commodity switches have essentially very limited memory. And we've done some back of the envelope calculation is that even the next generation of switches will not let us essentially be freely not worry about memory at all. So this is just part of the pain you have to take in if you start working with commodity switches. Okay, so the scalable allocation computation, it's basically what we do, as you might imagine, set up the problem. So we've got demand matrix from each services. We set it up as a path-constrained multi-commodity flow problem. A path-constrained version is essentially we route over a set of tunnels that are preset rather than letting flows go anywhere. And this makes the computation more scalable. And this also helps with memory stuff in there. And the other thing we do is, I'll talk about fairness in a second, but solving this at the granularity of individual switches and links tends to be very complicated. So we actually solve it at the granularity of data centers. So forget that there are 3 switches in the data center. We're going to merge that, do abstraction of the topology, and solve it at that granularity. But then we have to essentially map that configuration down to the network. And for that, we're going to leverage this inherent symmetry that exists in how the switches are connected. So that's basically lets the abstraction gets implemented as is on the switches by leveraging the network symmetry we have. So talking of maximum fairness, so maximum fairness, what we do is we achieve within a class, within a priority class. And the reason maximum fairness is computationally hard is because, so for a single resource, it's an easy problem. You just start from the bottom and start allocating. But network-wide, essentially, it becomes really hard because you need to do progressive water filling across the network when links are moved, and then you have to be willing to move the flows. It kind of struck me as a surprise. I didn't know that this maximum fairness problem was so hard. But it tends to be, and so there are like not enough, there's like very few algorithms that would scale to the level we need. So we kind of made up our own. And essentially what we do, take the entire space of allocations a service might have, and we do geometric partitioning of the space, and then we allocate in there. So what we have is fixed number of iterations, and we have bounds on how unfair we might be. So this is like an approximation of fairness that works within like a fixed compute time in there. Okay. By the way, I'm happy, I know I'm kind of glossing over details there, but I'm happy to talk to you about these things offline, or if you have questions, speak up. This for me was the favorite part of the work. So this is a problem that only arises in central allocation, and was like, essentially I didn't even realize network configuration would have this problem. Here's the problem. So suppose you wanted to change your network's configuration from the one on the left to the one on the right. And you may want to do this for any number of reasons. For instance, you want to free up capacity on the link R2, R4, as an example. Now the thing is, like, making this configuration change requires changing the configuration of R1 and R2 at the very least. Given that these are 2 different switches, you are not going to atomically switch them, or at least it's not easy to atomically switch both of them. Because you cannot do that easily, you may end up in the state of one of these states possible, where either R1 moves first or R2 moves its flow first. So no matter who moves first, you basically are now in a situation where you have a congested link, and the link is oversubscribed by huge amounts, and lots of traffic will get dropped in a burst. And this difference in the burst is a function of like what the time delay will be between R1 moving and R2 moving, and so to speak. So, and this is somewhat like I said, this is a problem unique to central allocation, because on the top we are dictating the network traffic when it's going north-south, and we say, okay, I don't like that, I want it to go east-west, and you want to do that essentially without dropping. So how do we address this? Yeah.
Just a clarification.
Yeah.
Also, the reason that R1 and R2 can't do something like two-phase commit is because they have limited resources, right?
Two-phase commit is not going to help you here.
Well, can't you just order your changes?
Can we order our changes? You may not be, under arbitrary circumstances, you cannot order your changes. So imagine a situation where the network is completely busy. All the links are used 100% of the time. Any first move will congest some link, right? And I think with your ordering thing, I think you're barking along the right line of thought. So that's what I think will become clear. But yeah. So this is what we do. So instead of trying to, so we want to do congestion-free network updates. So what we do is we compute essentially a congestion-free network update plan. So instead of going directly from left to right, we essentially take multiple steps. What I did not mention was that assume the capacity of each of the links is 1.5 times the size of the flow. So instead of going directly from the initial to final state, what I'm going to do is move half of FA, the blue flow, then move half of then move FB, and then move the other half of FA. So basically, don't go directly, but we compute a plan by which we don't actually rely on any kind of simultaneous move in there. Now the question is, like, can we always compute such a plan? Does it always exist or not? Here's what happens. So what we can show is that if we leave a scratch capacity of S on every link in the network, let's say think of S as being 10%, we can compute a plan that is at most 1 over S minus 1. So if S is 10%, this bound is basically 9 steps. On top of that, we can actually have like an algorithm. It's a linear programming based algorithm by which we can compute the plan with optimal number of steps. So what we find in practice is that we can have a plan that is about 2 to 3 steps most, even though when we leave S is equal to 10%. So here's what we're going to do. But the beauty of the problem here is that we actually have lots of background traffic. So we are not going to waste the 10% scratch capacity. Instead, what we are going to do is to use that scratch capacity for carrying just the background traffic. And once we throw the background traffic in, we can provide the guarantee that the amount of congestion that the background traffic faces is bounded, and no congestion is ever faced by non-background traffic. Dushyant?
These flows, they're kind of aggregated flows, right?
Yeah.
They're not a single TCP connection.
Yeah.
And I assume you move them in units of 1 to 5 tuple at a time, so you don't get multipath.
We build multipath through tunnels. We don't move them 1 5 tuple at a time. So think of it, we basically map, let's say, we move based on volumes. And that volume essentially could be decided by, so we decide, okay, there's like a 10 gigabits per second going between Seattle and New York, and I need to take 5 of this and park it, let's say, on a path that goes through Houston, as an example. And then we change the network configuration such that that actually maps to 5 gigabits per second. And what that actually means depends on the capabilities of the switch itself. If the switch offers us like a multipathing capability that lets us directly program the fraction of traffic that it should send directly versus indirectly, we'll go reprogram that. Current commodity switches don't let you do that, so we basically compute the prefix distribution, essentially a description point within the 10 gigabits per second that lets us move approximately 5 gigabits per second. James?
So you're trading off the possibility of not having simultaneous update and this consequent packet loss against the cost in terms of latency and throughput of you know this is the optimum, but we're not going to do that yet. We're going to do this, then this, and this. What's that trade-off? I mean, I'm just a tiny bit skeptical that you can't get 2 switches to synchronize their clocks and change behavior at the same time?
It's not about synchronized clocks. It's also about when you apply a rule, what we are learning is depending on how busy the switch is, it can take anywhere between, after I send the switches command, it can take anywhere between 200 to 300 milliseconds for the effect of the rule change to happen. So the variation you might see is not purely limited by clock synchronization. It's also limited by other things. And what we've also done, even if you forget this variable delay, what we've, based on real traffic, what we've kind of learned is that anywhere between 0 to 100 megabytes of extra traffic can arrive at a link in these time differential periods. And if you have router buffers that are of the order of 10 megabytes, you'll essentially see a huge drop in traffic, virtually highly bursty. Now you have huge TCP windows. They'll see a burst that goes through, and they'll back off. So that's actually that back off, and then TCP is gonna take time coming up. So that's the other thing we kind of worry about. Those second order effects that will happen due to highly bursty losses there.
Right, but here's another way to think
Yeah.
about it. At 40 gigabits per second, even if you atomically synchronize the switch change in Los Angeles and the switch change in Tokyo, there's still an awful lot of bytes traveling across the Pacific that are going to arrive at the other side after you've already, that are already in flight. Okay, they're just going to slam into the traffic at the other side.
Tish?
The property that you provide that background flows will not have bounded congestion, and foreground flows will not have congestion at all. Seems like a very nice property. It's not obvious to me where it's coming from, right? Because you're probably relying on priority support at these commodity switches.
Yeah.
Right,
So we
the
are
priority-
relying on the strict priority queuing. So I think, yeah.
So this priority, what you'll get is priority on forwarding, but not priority on buffer sharing. And if you don't get priority on buffer sharing, which applies to almost all commodity switches we have experimented with, what you'll find is that the buffers will be filled with background traffic, which means that the foreground traffic comes and you'll see losses. So I don't know how you actually got across the...
I think in the experiments we've done, we haven't looked too much, I should say, like to tell apart. My understanding of priority queuing is that basically that essentially maps to buffer priorities as well. If a packet arrives, if it's an interactive traffic, it basically gets priority, it gets its own queue, and it gets sent. And this is strict priority. This is not weighted priorities. These are strict priorities. So what that means is, like, as long as the switch has an interactive packet to send, it will send it. If not, it'll move on to the next category, next priority class, and next priority class.
I guess the problem comes from the fact that most of these switches have shared buffers, and it's very hard to have dedicated buffering for the priority class. But I can probably,
okay.
and I'm sure it's a corner case or...
No, it's good to know. I don't think we've seen that, but if it happens, we can go looking for it, actually. So that'll be a good point to make, yeah. Okay, so the third thing was working with limited switch memory. I'm going to touch only kind of briefly on it. So here's what we do. So the challenge here is that we are directly programming these flows. And these flows, they can have highly complicated L3 filters. So, a service could be described, for instance, by, I don't know, like 10 prefixes and source and destination. And we kind of get limited by how much memory these switches have. So we do two things. One is that we use tunnel-based forwarding. So that essentially means that we are not going to use IP-based filters, IP address-based filter anywhere but where the flows enter. So take that filter table, and then from there on, we essentially say tunnel 1, tunnel 2, tunnel 3. It's a label that gets carried in the packets, and the intermediate switches just work off of that label instead of 100 rule description of the flow. So they just work off that. Even that's not enough, in fact. So because that's not enough, so now we essentially think we basically kind of take the working set idea that it's not like you need all possible tunnels at any instant in time. Yes, you need a lot of tunnels in the network across time, but at any given point in time, you don't need all of these tunnels. So think of Y working set of a process is a lot smaller than its total memory allocation. So kind of same thing actually happens in this network traffic, because the demand matrix has temporal variations and so forth. So what we do is that we basically greedily pick the tunnels that essentially can carry the traffic right now, and which is kind of the working set, and we keep only the working set in memory of the switch, and we rotate this, and we've got mechanisms to rotate the working set. Vish?
What's the size of the problem? As in, are we talking about, because if you have n data centers, you're talking about n square maximum possible tunnels, right? If n is 50, isn't that 2,500 maximum?
If n is 50, no, because if you have n data centers, you need tunnels between n square pair of data centers. Now it's a matter of how many tunnels you need between two data centers. So if you want 10 tunnels, so we operate our MPLS with 10 tunnels between every pair of routers. So you see where the scaling problem is coming from. Yeah. And in general, we find like even like if you wanted like the total allocation, so continuing the process analogy, it maps to basically that we need K, where K, if we need K shortest paths, we need about 15 tunnels to essentially fully use the network. And we cannot support 15 tunnels between every pair of DCs. But the thing is, the beauty of the temporal locality of traffic is that we can actually do with only 2 or 3 at any given point in time, as long as we can quickly identify and keep those 2 or 3 in memory in there. So the way we rotate this is actually very, very similar to the way we do stuff, to the way we do like congestion-free updates. By the way, the problem with changing the tunnel set is we must add a tunnel before we can remove it, because every tunnel is carrying traffic at any given point in time. So if we remove the tunnel, all the traffic will get dropped. So we need spare capacity in the memory to first we should add, and then we should delete the tunnels. So you've got to retain that. And to do that quickly, we keep essentially a scratch capacity lambda in the memory of the switches, and then we get symmetric results that the maximum number of steps to add a tunnels would be essentially 1 over lambda minus 1 in there. So again, lambda is 10%. We can, in maximum of 9 steps, again, in practice, it's a lot smaller. But one difference between congestion-free updates and this one is this is essentially a discrete problem versus the flow problem. So essentially, the algorithm we have is greedy but not optimal. But in the congestion-free update case, we have an optimal algorithm. This one's just greedily select stuff. There. Okay. In case now if you're all confused what all is going on, this is what happens in the entire system. Every 5 minutes, we compute bandwidth allocation, network configuration. We compute how the rule change. So this is the tunnels in the memory will change. We compute what I call like the bounded congestion plan to change. We notify services that have, so this is steps 1, 2, 3 are purely computational. At step 4, we tell services who have a reduced allocation to lower their rate. Step 5, update the network. Step 6, some services would have higher rates. We tell them, okay, now you can go up now. And this is what time, if you're curious about how much time it takes each step, and this will tell you like, essentially, our bottleneck right now is distributed rate limiting. So if you see like the two biggest, the long pole analysis is like how quickly can we get an entire service, which could be thousands of hosts, to speed up or slow down. The other thing is, and this is essentially data-driven simulations. So we've taken real demand matrix and stuff, and it's modeling switch delays, but it's doing a predictable model of switch delays. So, but that 0.6 seconds, so 600 milliseconds is the number when the network is actually in flux. And this is kind of reflective on how quickly we can actually update the network on the congestion plan. James?
The first wait for rate limiting is waiting for the services which have reduced bandwidth to slow.
Yeah, right. And the second one's, waiting for them to ramp up. So if we had, you guys have been working on faster rate limits. So if we can get like that control loop going faster, we can actually do this a lot faster than you have. Okay, yeah.
0.6 is to change switch rules 8 times, the steps, all 8 steps, or?
All the steps.
All 8 steps?
Yeah. What do you mean 8 steps?
But you said there's a bounded number of steps, right? You'll have 9 steps. So, because you'll do the steps separately, right?
Yeah.
So is this 0.6 for one step?
The entire change. The entire change.
Do you run into
These are averages, yes. Yeah.
You run into what Richard raised earlier, which is, that 0.6 seconds, the amount of time to send stuff across the Pacific or, the longest links is a significant fraction of that. So when you change the switch rule, you need to wait for all the in-flight traffic to finish before you can change.
No, we don't have to wait for in-flight, because the way we compute what happens in a step is based on a worst-case analysis. on every link. So this is where the scratch capacity helps us. The worst case analysis is that basically, so we are taking a step, right? So worst case analysis say, okay, the traffic on the link will not have moved away before new traffic arrives. So all of these updates essentially within a step get applied in parallel, and we have a guarantee that congestion will not happen. Then step 1 ends, we get all the acts back, then we begin step 2 within the update plan, and that step 2 goes in parallel, comes back, step 3 starts, and typically we need only like about 2 or 3 steps.
So the fact you're waiting for acts to come back means that the in-flight traffic can finish because it takes the same amount of time to stop being in flight as the acts come back. Yeah.
So just curious, what's your utilization when the network is in steady state? I guess it's not 100%. What do you keep it at?
I'll show some results. Yeah. So here's what we built. Essentially, we have a system running in a lab close to MSR, Building 99. We work with the first generation of prototype we built worked with open flow switches, a mix of blades and aristas. Blades are horrendous, by the way. These are like IBM's open flow switches. I don't recommend buying them. Aristas are a lot better if you're in the market for open flow hardware. And we worked with this big switch open flow controller. We started using 32 servers with each server running 25 VMs. And so essentially we get a lot of statistical multiplexing going to do the prefix-based tricks we're talking about. And essentially the prototype also contains some number of routers and stuff. Okay, so on to results. So yeah?
The failure cannot be detected before the 5-minute interval, right?
Sorry, what?
The failure cannot be detected before the 5-minute interval.
No, so failure notifications come from the switches to the network agent, and we react to failures right away. So that's what happened there. Like, so what we find is right now the biggest delay is discovering. Essentially, the link has gone down on the switch itself. That's just a limitation of the way LLDP works. But the faster notification, I think failures you have to react right away. Otherwise, you will end up dropping a lot of interactive traffic as well, which is completely non-starter.
And the 5-minute interval comes from what? Collecting the statistics, or is it the expectation that traffic is kind of?
I think it's the fastest we could go and evaluate at that scale. In the sense, what we've done is some experiments on that if we change 5 to 10, what we learn is that we lose about 2 to 3% utilization, which, you know, from a research perspective is not more, but from an operational perspective, it translates to, you know, 3 full-time employees, like in terms of the amount of money. So what we know is that, like, going from 5 to 10, we'll lose efficiency. What we don't know is that whether we can go faster than 5 and what the gain would be. And part of the reason for that is that we have traffic statistics that are 5-minute granularity. We don't know what they look like at sub 5-minute level, so we can't even do that evaluation until we have something kind of deployed fully. Yeah, they're net flow, but the granularity is 5 minutes, yeah, or S flow, the standardized net flow, yeah.
The target scale, is that 20 data centers or 200 data centers?
I don't think it's going to be 200 data centers. Think of 25 as a number.
So that 5 minutes seems like an awfully long time. And going back to your arguments about, you know, we have to do this funky thing for max-min sharing, seems, as in I thought the trick was very neat.
Yeah.
For 25 data centers, just seems like...
It's not 25 data centers. It's between each pair of data centers, there are hundreds of services. So the allocation is happening at that granularity. So the fairness is between services, right?
One max min, if you do the water filling, it's a function of the number of nodes in the graph and the number of flows. I just find it hard, given that you're dealing with aggregate flows, I find it hard to imagine that simple progressive filling would take forever. But maybe you'll talk about results.
I'm not going to show the fairness computational results. I think the numbers you showed for computation, the only thing that was indicative there, I think we tried to do it the direct way, and we could not get the computation to scale. Maybe if we talk to LP experts, there was a way to formulate it. But the thing is, the problem is progressive water filling has the following problem. Let's say you have, take the case of 25 data centers. So now you have, what is 25 times 25? Like 625. So you got 625 flows. Thing is, you pin each flow at a time. So you pin the lowest one then. When the link fills up, you have to be open. You're basically doing almost factorial computation because this is a network-wide allocation. Here's what's going on. Like you pin, a link fills up, so you know that's the max capacity. But when you take the next step, you have to be open to unpinning this flow and moving it somewhere else. And that's where a lot of the complexity comes from, progressive water filling in a network context. And you never have to do that if you're doing single resource allocation in there. But I think there are entire theory papers on trying to solve this problem. I think we implemented one of them and it was too slow for us. But if you have better ideas, I think that would be helpful, yeah. So this is a result on one of the networks. Since this public forum, can't say which. So we took real topology, real traffic on this network, and what I'm showing here are 3 bars. So MPLS-TE is essentially the state of practice today, and if it worked really well, this is what the red line would be. And the blue line is essentially SWAN. So what we see is that we can actually carry 60% more traffic on the same network, essentially. So this is like we have some deployed capacity and how much more traffic we can carry. So we can carry 60% more. The green line is somewhat interesting because it shows like a variant of SWAN where we only have centralized resource allocation but no ability to rate limit at the edges. So think of somebody like, I don't know, BT or AT&T. They don't have the ability to shape traffic, but they do, in theory, have the ability to centrally control resources. So if you had just central control of resources, where you reconfigured your network based on whatever's coming in, you're not controlling what comes in, you still see like about half the gain. So what that means is that of the total gain that's happening with SWAN, based on coordinating rates of services and central allocation, the gains are roughly equally split from central planning as well as coordination across services. So you could take this and apply to AT&T and they'll see this much gain. But of course, in a Microsoft, Google kind of context, we'll see even more gains because we have the ability to control what enters the network. This is now beginning to touch on essentially what happens, why we actually need congestion-free updates. What the left graph is showing is that what is the oversubscription ratio of a link if we were to do one-shot updates. Just don't worry about congestion. Just send all the updates. Go from initial to final state in there. The orange line is what happens to background traffic with one-shot updates. The red line is what happens to non-background traffic with one-shot updates. So what you see here is that if you look at, I think the non-background traffic is kind of more interesting. What we see is that oversubscription ratios for non-background traffic, which includes interactive traffic, can be about 20%. And if you do the math, what that means, that 20% over, so 20% here means that 1.2 times the link capacity amount of traffic is coming on the link. If we take that 1.2 times and we actually multiply by the time that oversubscription lasts, what the right graph shows is how much traffic ends up at the link, how much more traffic than the link can carry ends up. So what you see here is even non-background traffic. In this case, you'll basically see cases where 50 megabytes of non-background traffic ends up. And in the background case, can go up to like 200 or 300 megabytes of traffic will come. And all of this traffic will essentially get dropped in a big bundle. So this is kind of like why we had to do some kind of congestion-free planning in the first place. OK, this is essentially where we are right now, I think what I just described. Where we are headed with this is we are in the middle of getting optical capacity to do this deployment in the wide area. So go outside the lab and get optical capacity and start running these things in the wild because we believe we'll learn something extra there. Most of the technical focus of the work at this point is, and which I showed like I think basically these are the kinds of topics our interns are working on right now, and they're all related to resilience to failures and uncertainty. What I mean by the description of failure, what I mean by uncertainty is the following, that like, so far we've assumed we have perfect knowledge of the demand matrix. We have perfect control that when we tell a switch to update a rule, it actually updates a rule. I think the reality is a lot more complicated, that we'll essentially have highly imprecise control. So if I ask a switch to send red-colored packets left, we don't know how much time it'll take for the switch to do that or whether the switch will do that or not. So that's what I mean by kind of imprecise control. So right now, I think we're doing a lot of kind of algorithmic work on dealing with this imprecise control and uncertain information in this context. And that's where we are at this point. And in terms of, I think, a deployment plan, it's rather simple because we can play at the optical level. Essentially, what we can do is just split off the optical capacity and deploy a WAN essentially in parallel to the one we have today, and slowly move prefixes from the top, which is our Juniper-based WAN, to the commodity WAN. So without having a flag day, we can have essentially parallel networks and slowly move all traffic from the traditional wide area network to SWAN, essentially. Okay, to summarize, essentially talked about SWAN. The goal was to yield highly efficient and highly flexible wide area network, and we achieved that by coordinating transmissions of services and centrally allocating resources. What was hardest for us in trying to build this system was to managing transitions. I think computing allocations was a computational issue, but how to actually every 5 minutes compute bandwidth allocations and every 5 minutes change network configuration and do that in some sane way without losing traffic or without blowing away the memory at individual commodity switches. The last thing is generally, I think to me it was kind of revelation. In the past I have not worked on efficiency or performance related things. I think one thing at a very high level, one thing I've kind of learned from this is like, I think if you're talking, there are a whole bunch of interesting issues now in the space of efficiency with cloud services, because it's not purely about efficiency. A lot of this stuff is beginning to touch on competitiveness, and running large scale cloud services is at this point is turning to cost. Whoever can deliver the cheapest infrastructure is going to win out in there. So I think there's a whole bunch of work to be done in, as not just Microsoft, a lot of companies are building out the cloud services and eking out efficiency from the infrastructure. So I think this was just one example, but there are lots of other examples within a data center, as I think, or server utilization and so forth, where it directly touches the bottom line of the company, and which is kind of, which is great for systems researchers at least. Okay, with that, I'll end. Thank you.
Any more questions? Yes, I'm quite surprised that you recompute the allocation from scratch without looking at what you had allocated before at every round. So I would like to have an idea of how moving that is, whether you switch configuration completely between stages and whether there is a way to be more incremental or continuous in the changes that you push to the network.
I think that's a great thought. If we can get that without programmatic complexity, we'd love to have that ability. Right now, I think you're right, we solve from scratch, and there are mechanisms you can take LP to its dual form where incremental computes become easy. The reason we did that is essentially it was easy to program, that we could throw it at regular solvers. At the same time, I think we have talked to some people who specialize that, and I understand that we can essentially get a lot of the gains by solving the LP as we are doing, essentially take it to its dual domain, where we can, without much programmatic complexity, we can get back the benefits in there. We have not built that yet. I think because once we figured out we could do the allocations in under a second, in some sense, I think we had less of a motivation to improve that computational aspect in there. But maybe if we start scaling or if we start doing things, we'll look at it again. But if you have kind of good ideas what we might do, I'm kind of happy to talk to you offline. I think as we talk about, like, I think the topology abstraction bit we have is right now has a cost. So one of the, if I had a super fast solver, one of the things I would do is to not work on an abstract topology, but actually work on a real switch and link level topology. But that blows up the number of constraints and number of constraints and variables in our LP by a factor of 16 or so. And that increases LP complexity by, if LP is, n to the power of 3. So then it's too much. I think if there was some cheaper way, if it was so cheap that I can actually solve the LP on link level topology, that'll be great. We can go there. And I'm happy to talk to you offline for any ideas on that front. Yeah.
So follow-up.
Yeah.
I'm a bit confused. I thought that, so how long does it take to actually solve the LP now? Is it 5 minutes is for that, or for actually estimating traffic and making sure you get the inputs for the LP and all that?
Solving the LP right now takes 1.3 seconds. This is solving the LP. Actually, it's not just one LP. It's like even like congestion-free update planning is an LP. It's a sequence of LPs. All of that is 1.3 seconds right now.
So why do you care so much about updating? I mean, it's not really getting to the waiting for the rate limit and everything is the more of the overhead.
Yeah.
And you could put that onto, I don't know, more machines or something, scale it up or something.
The LP?
Yes. You do not like try to parallelize some bits of that and.
We are just using off-the-shelf solver. I don't know how to parallelize that.
Do you see that as a really key thing to be improved?
No, so we are not. So that 1.3 second number, that's what I said, we are not trying to improve right now. But what I said, like if I actually had, let's say, 2 orders of magnitude faster way to solve this, I would solve a different LP that is higher fidelity. So right now we solve the LP at the granularity of data centers. If you gave me a method that was 2 orders of magnitude faster, I would start solving an LP that was higher fidelity and worked at the level of switches and links. That's what I meant. Yeah, so this 1.3 second number, we are not interested in improving, no. Yeah. James?
See analogous problems where it's the same solution can affect, like, I don't know, mesh wireless networks? Or presumably those sorts of problems are already tackled, so.
So what would be an example of an analogous problem?
Take a sort of a wireless mesh network where you've got sensor flows or whatever going around, and things change, and you're changing the routing to cope with that, right? It's a similar sort of setup to here.
Yeah. So I think the difference here is, like I said, I think I don't know if a system. I think the problem will come up there if you start doing centralized planning and running your links hot. A couple things go on with the wireless context. I think it's also unknown, right? Like, what does it mean to run like a wireless mesh network hot? The capacity models are incomplete, so you don't even know how much you can push it. And the other is, like, most of the work has happened with distributed resource allocation there. So distributed resource allocation, we haven't seen that problem. But I think if people started doing wireless mesh networks with centralized planning, and they got an idea of what a capacity there even means, then I think some of the same things will apply in the sense of the challenges they will face, and maybe some of the solutions will work out as well there.
Other analogous domains that fit better? I just want you to build those really nice tools. So, what other?
I don't know yet. Yeah. I think there are. I think the domains we've kind of looked at, I think the details end up being so different that we don't know. I think there's certainly a problem within the data center to updating traffic, but the scale we are talking there is so huge that my sense is people will end up designing approximate schemes rather than the precise theoretical guarantee we are offering with updates. I think that our kind of computation will not work there. I think this thing carries over. I think in the new work we're doing, I think this way of looking at things is actually helping us even, at least in this domain, in reasoning about imprecise control as well, because like I said, alluded to, in the construction of the LP, there's this notion of worst case. So we can embed that, and it's helping us solve other problems within this domain. But I don't know of another domain where the same thing directly applies. Thomas?
Maybe you mentioned it, but I missed it. So what is the wait for rate limiting exactly waiting for? Is it like,
It's, I didn't mention it. It's basically depends on the period with which. So what's happening is that service brokers, they don't call back into the hosts that change your rate because we didn't believe we could build a system. If you are controlling thousands of hosts, you could reliably contact each one of them to slow down or speed up. So instead, what happens is that these hosts, they sit in a loop, which is 10 seconds. Every 10 seconds, they go to the service broker and they say, how much can I send? How much can I send? So after the SWAN controller tells the service broker, hey, your capacity, your throughput should go down from 10 to 5. The service broker knows that immediately, but because the hosts are coming every 10 seconds, it can take that much time for that thing to get implemented. Yeah, you guys are experts at distributed rate limiting, so that's one of the things I think we'd love to improve if there's a practical way to fit that in.
Any more questions? If not, let's thank you again.
Thank you.